This is Algebra 3, Prerequisite Chapter, Section 5, Rational Expressions. The domain of an algebraic expression. Okay, a few terms here. First of all, the domain is the set of real numbers on which the expression is defined. Or another way of thinking about it is the domain consists of all the x values that are okay to use in the expression. Now, equivalent. Two algebraic expressions are equivalent when they have the same domain, so they can use all the same x values and yield the same values for all numbers in their domain. In other words, when you put an x, a certain number in for x for both expressions, you end up with the same answer. For example, x plus 1 plus x plus 2 and 2x plus 3 are equivalent. And if you're wondering why, combine the x plus 1 and the x plus 2, and you see that you get the exact same expression as 2x plus 3. Okay, our first example, you're going to state the domain of each expression. What x values are acceptable to use? Think of the limitations that you have to put on x because of things like roots and fractions. Pause the recording, try the exercise, and then check your answers. Okay, so for A, it's the set of all real numbers. It doesn't matter what x you put in there, you will get an answer. So with any polynomial, actually that's going to be the case. So unless they specifically tell you to restrict the domain, you can use all values for x. Usually you're going to be restricting the domain when the polynomial is part of a real-world situation where negative numbers maybe don't make sense or certain values for an answer would not make sense. Okay, B, we've got a square root, and what you need to remember with roots, specifically even roots, is that you cannot have a negative number under that radical sign if the root is even. So we need to take out all values that are going to give us a negative. Now 0 is fine. So as long as x is greater than or equal to 2, we're good. Anything less than 2 is going to give us a negative. And finally, C, we have a fraction. And what you need to remember, and we forget so easily, is that with fractions, you cannot have a zero denominator. So what we need to do for C is to ask ourselves what value for x will give us a zero denominator. And that would be 3. 3 minus 3 would be 0. So the domain for C is all real numbers except x equals 3, because that would result in division by 0. Now when we have a quotient of two polynomials or two algebraic expressions, that's called a rational expression. You have a few examples there. Recall that a fraction is in simplest form when the numerator and denominator have no factors in common aside from plus or minus 1. To write a fraction in simplest form, all you need to do is divide out the common factors. So the key to success in simplifying these things is going to be your ability to factor polynomials. In fact, we're going to rely on factoring quite a bit this entire year. So it's really important that you get the factoring down and that you practice it and make sure you've got it down well. When you're simplifying rational expressions, factor the polynomial on the top, factor the polynomial on the bottom, see if there's anything in common, and then you can cancel if there is. So here's an example. I want you to try this. Remember, what you're going to do is factor the numerator, factor the denominator, and then only cancel common factors. Pause the recording to try it and then resume recording to check your answer. All right, so the first step is to factor completely. The top factors into x plus 6 times x minus 2. The bottom factors into 3 times x minus 2. The x minus 2's will cancel and leave us with x plus 6 over 3. Notice we are making the statement that x cannot equal 2. You may think, well, that's kind of weird. When I simplified it, I didn't have x in the denominator, so why does it matter? Whenever we are giving the domain restriction on a fraction, you always give it for the unsimplified fraction. So even though in the end, after we simplified it, we didn't have an x in the denominator, we started out with one. You need to go with the original equation to figure out what numbers you cannot use for x. If you were to put the unsimplified version in your calculator and graph it and then look at the table, you would see that for x equals 2, y is undefined. Okay. Now this is just a word about how the book does things. It says in this text, when writing a rational expression, the domain is usually not listed with the expression. It is implied that the real numbers that make the denominator 0 are excluded from the expression. Even though this is true, when you simplify it, you do need to show the domain like we did on that last problem. Also, when performing operations with rational expressions, this text, the book we use, follows the convention of listing by the simplified expression all values of x that must specifically be excluded from the domain in order to make the domains of the simplified and the original agree. So even though on the original they're not going to tell you x can't be whatever, they're saying that's implied by the problem itself. When you simplify it, because you've changed things, you must put the restrictions on the domain by your simplified expression. That's to make sure that the original and the simplified agree. All right, when we're working with rational expressions, we're going to really just use the properties of fractions. When you multiply or divide, when you multiply, you just multiply top times top, you multiply bottom times bottom. When you divide, you're going to do keep, change, flip. You're going to keep the first one, change it to multiplication, and flip the second. To add or subtract, you do need to find a least common denominator, or you can make it a little easier on yourself by using the basic definition that they have listed here. Notice what they've done. They've said a over b plus or minus c over d. In order to get the common denominator, what they really just did was they multiplied by the opposite denominator. In other words, a got multiplied by d, the denominator for the second fraction. C gets multiplied by the denominator for a, the b. So you have AD plus or minus BC on the top, and then on the bottom the two denominators just get multiplied together. This is a really quick way of doing it. Sometimes it's the best way, sometimes it's the longer way. So it just kind of depends. If you have troubles finding the least common denominator, this is a great way to go. Definitely if your denominators don't have any common factors, you want to use this method. All right, a couple of examples. The first one we're going to multiply. The second one we're going to subtract. Let me remind you that when we multiply these rational expressions, we do want to factor the numerator and the denominator. With adding and subtracting, if possible, you want to factor the denominator first. With multiplying and dividing, you factor both. All right, pause this recording, try the example, and then resume to see the answer. All right, here are our answers. A little overwhelming, I guess. Sorry about that. But if you start at the top, the first thing we did was we factored everything in both fractions. So the 2x squared plus x minus 6 becomes 2x minus 3 times x plus 2. X squared plus 4x minus 5 becomes x plus 5 times x minus 1. X to the third minus 3x squared plus 2x. You actually need to factor this in two stages. They have the common factor of x, which gets pulled out. And then what you're left with, x squared minus 3x plus 2, factors into x minus 2 times x minus 1. In the denominator, we only have a common factor of 2x, so it's 2x times 2x minus 3. You'll notice that the common factors have been canceled, one on the top and one on the bottom. It doesn't matter whether or not they're in the same fraction. What matters is that you can only cancel a numerator factor with a denominator factor. You cannot cancel two factors that are both in denominators or both in numerators. So the 2x minus 3's go away, the x's go away, and the x minus 1's go away. Notice in our final answer, we didn't bother to multiply everything back out together. It's really not necessary. It's extra work. Don't do it. So on the top, we have x plus 2, x minus 2, and then 2 times x plus 5. Now, if you look at it, at the restrictions there, you'll notice they left out -5. Well, -5 is clear from the simplified version itself. It's not going to be in there. But what's not clear are the ones that got canceled out when we multiplied. So in the original problem, x could not have been 0 or 1 or 3/2. Those would have given the original problem denominators a 0 and made them undefined. -5 would have done that also. However, in our simplified format, -5 is already there. We already know from that we can't use -5. All right, the second one, we use that method of kind of we're not really cross multiplying, but it sort of looks that way. The x gets multiplied by the 3x plus 4, the -2 by the x minus 3, and then the two denominators come together on the bottom. Now, you want to leave the denominators factored, but you must go ahead and multiply and distribute out the numerators, combine like terms. If you can factor the numerator, it's a good idea because you may be able to simplify further. Notice that we don't list any restrictions here with the answer, and that's because the original restrictions, x can't be 3, x can't be -4/3, that were a part of the original problem, are still going to be a part of this problem. There are no changes there, so we don't need to list any additional restrictions. The previous method we used worked well when you have only two fractions, and really well when those two fractions don't have any common factors in the denominator. Now, if you have common factors in the denominator, or if you have more than 3 fractions, you're really going to need to find the least common denominator. Just recall that the least common denominator of several fractions consists of the product of all the prime factors in the denominators, with each factor given the highest power of its occurrence in any denominator. And then here's an example. So we have 6, 4, and 3. Okay, our common denominator is going to be 12. Okay, it's 6 times 2 is 12, 4 times 3 is 12, 3 times 4 is 12. Whatever you multiply the bottom by to get your new denominator, you must multiply the top by to get the new numerator. And then you see that in the bottom there. So we have 2 12s, 9 12s, minus 8 12s. Combine the tops, we get 3 over 12, and then reduce it to 1/4. Next we have complex fractions, or I like to call them double-decker fractions. It's really a fraction within a fraction. It may be that you have a fraction in the numerator of a fraction, in the denominator, or both. The first example here has a fraction in the numerator, and the second has the fractions in both. To simplify them, what we're going to do is we're going to combine the fractions in the numerator into a single fraction, combine the fractions in the denominator into a single fraction, and then what we can do is just remember that a fraction is really a division problem. So we'll change it to a division problem, and then we will do keep, change, flip, and multiply. So for example, our second fraction here with the 1 over x over 1 over x squared plus 1, what I would do is I would say that's 1 over x divided by 1 over x squared plus 1, and then change it, 1 over x times x squared plus 1 over 1. And that's going to make it a lot easier to simplify. Here's an example to try. Don't forget you want to combine the numerator into one fraction and the denominator in one fraction. Last year in Algebra 2, we learned an alternate method, which was to find the least common denominator for all the little individual fractions and multiply everything by that. If you remember that and you prefer that, you may do that also. Pause the recording, try the example, and then resume to check your answer. Okay, this uses the longer method. We're going to combine the fractions first. So we have 2 minus 3x over x. What they did was they gave the 3 the common denominator of x, and when you put an x in the denominator, you have to give it to the numerator. We did the same thing on the bottom. X minus 1 became the common denominator. And then we simplified that, so we have 2 minus 3x over x on the top, and x minus 2 over x minus 1 on the bottom. And then we're just going to make it a division problem. And we're going to keep change flip. So the top, 2 minus 3x over x, times, and we're going to flip that denominator fraction upside down, x minus 1 over x minus 2. Then just combine them. Notice that there's nothing that can cancel. We're not multiplying everything out. We are making the point that x cannot be 1. Now you'll notice that x can't be 0. X also cannot be 2. That's obvious from the simplified form. However, we need to add in that x cannot be 1 because if you look at the original, on the denominator, we have 1 over x minus 1. So that denominator there cannot be 0. And I forgot to mention x also cannot be 0, but that's also obvious from the problem itself. So another way, and this is the second method I mentioned, you may remember from last year, another way to simplify a complex fraction is to multiply the numerator and the denominator by the least common denominator of all the fractions in the numerator and denominator. This is the exact same problem we just did in the example. And so instead of combining the top and combining the bottom, what we do is we say, all right, look at these individual fractions in the numerator and the denominator. In the top, we have a denominator of x, in the bottom, x minus 1. That's going to become my least common denominator. What I'm going to do is multiply the top by that and the bottom by that. So on the lower part of the screen there, you see where we've done that. In the numerator, the x's cancel and leave us with 2 minus 3x times x minus 1. And in the denominator, we're left with x times x minus 2. Same answer. Most people find this to be a little faster and a little easier, but in the end, it's kind of up to you, whatever works best for you. You might have an expression with negative exponents, and rather than trying to deal with it by changing them to fractions, taking the negative off the exponent, one method you could use is to begin by factoring out the common factor with the lower exponent. And remember, when we factoring is division, you subtract the power. So for example, we have 3x to the minus 5 halves plus 2x to the minus 3 halves. The lesser, the further to the left, the number further to the left on the number line is going to be negative 5 halves. So the common factor is going to be x to the negative 5 halves. So you pull that out. When you divide 3x to the negative 5 halves by x to the negative 5 halves, you get just plain old 3. When you divide 2x to the negative 3 halves by x to the negative 5 halves, what you have to do is subtract those powers. So we're going to have 2x, and our power is going to be whatever negative 3 halves minus negative 5 halves is. Well, if you go ahead and do the math there, it's negative 3 halves plus 5 halves, which is 2 over 2, which is 1. So we have x to the negative 5 halves times 3 plus 2x to the first. And then we can go ahead. We really don't want to leave a negative exponent in our answer. So in the very end, we want to go ahead and put in the denominator the x to the 5 halves. Again, we don't have to mention that x cannot be 0 because in the original problem, x could not be 0. Both of those x's had negative exponents. They would have been in the denominator. So it's understood from the original problem that x cannot be 0. Oh, this looks like a really fun example. So why don't you give this a try, pause the recording, work your way through it, and then resume recording to check your answer. Okay, it's a little intimidating, but let's not worry about that too much. Let's look at what's going on here. The first thing that we are doing is we are multiplying top and bottom by 4 minus x squared to the 1/2. Now you may wonder, why are we doing that? Okay, that's going to help us get rid of that negative 1/2 power on the top. It's kind of a mess. It's all in there mixed up with everything else. So we're going to multiply that to get rid of it. And when we do, when we FOIL it out, we get 4 minus x squared to the first, because multiplying the 4 minus x squared to the 1/2 to the very first term, 4 minus x squared to the 1/2, is just going to give us 4 minus x squared to the first. When you multiply, you add the powers. When we multiply it times x squared times 4 minus x squared to the negative 1/2, add those powers, we get 0. So it's x squared times 4 minus x squared to the 0 power. When we multiply the denominator, we have 4 minus x squared to the first, and we're multiplying it by 4 minus x squared to the 1/2. Add 1 plus 1/2 and you get 3/2. Okay, the third line down, we're just cleaning that up a little bit. That gives us 4 minus x squared plus x squared. And then on the bottom, we have 4 minus x squared to the 3/2. And then finally, the minus x squared and the plus x squared cancel out and just leave us with 4 on the top, 4 minus x squared to the 3/2 on the bottom.